Oh, sorry, I couldn't tell if it was recording or not. Sorry, normally it'll say, "Hey, this is recording." Um, okay, just making sure my sound it wasn't the issue. But hey, welcome back to Behavioral Statistics. We are moving into our chapter on variability. We covered measures of central tendency, and now we're going to switch gears and look at variability, which is a really good follow-up to measures of central tendency, because measures of central tendency tell us one thing about our data, but it doesn't quite tell us the full story. We also need to understand variability, how the data varies. So these are the learning outcomes. By the end of this chapter, you should be able to understand the purpose of measuring variability and also including various strategies of measuring variability, including range. So you need to know what range is and how to compute it. You need to understand variance and standard deviation related to that, calculating the sum of squares, referred to as SS. Variance, standard deviation of population, same thing then when we're referring to samples. So again, we're talking about stuff, with samples and populations that came up in the very first chapter. So hopefully, seeing those two terms pop up again, it's not, not it's not surprising. Seeing those terms, because they're going to come up again and again. So, what are some things that you will need to use for this particular chapter? We're going to come back to summation notation, and then we will bring in some elements of measures of central tendency, mean and median. So, we're referencing back to a couple of previous chapters, like usual. So this is what I mean by, measures of central tendency don't always tell us the full story. Like right here, we have in this picture, we have two graphs, two images that have the same mean, but are clearly not the same picture. Like the data is not distributed the same way. Now, they're both a normal distribution, I should say, or both examples of a symmetrical of a normal distribution. But notice there's something very different about both of them. One is more peaked than the other. One is a little more flattened out than the other. The red one is a little more flatter. The blue one's a little more peaked. Now, if you go down to the chart, we can see they both have a mean, an average of 50, but they have what is called, this is SD is short for standard deviation, and both are different. The standard deviation for the red one is 10. The standard deviation for the blue one is 5. And basically, what that means is we have more variation. The higher that number, the standard deviation means we're seeing more variation in the data. So we're going to start with just defining what variability is, and then all we're talking about is the statistical measure of spread or deviation from our mean. Like how much is our data on average? How much is it deviating from the actual mean? Now we refer to any kind of deviation in statistics as error. That doesn't necessarily mean good or bad. Like there's no value judgment. There's no, it's not like somebody made an error. It's just that's how we think about that word in statistics. So what we're trying to understand is how variable is our data? How well does the measure of central tendency represent the data? How far away from the measure of central tendency are our data? Is the data more clustered together, more spread out? So if you can see in the previous slide, the blue one, we have much more clustered data. The red chart, we have more spread data. And that's what we're trying to capture statistically. Because averages, they can kind of be misleading. They only tell us a part of the story. So what we're going to do is look at how we can present the full picture of our data and the common measures of variability that we're going to look at: range, interquartile range, variance, and then standard deviation. So here's just a way of thinking about variability, just kind of a thought experiment or just something to think about and why we want to consider variability. So if I know that the mean exam of a score is 70, would a 87 be unusually high? Knowing, okay, 17 points higher than the average. Well, it depends on the variability. If our data, ranges from 40 to 100, then maybe not. Maybe that isn't so much of an unusually high score. But if the data typically, like if we're seeing more of the spread is around the 65, 75 area, then probably so. That kind of gives us understanding variability, gives more context to this score in this particular setting. So we can define variability in several ways. It's a quantitative distance from our measure of central tendency. So basically, what this is doing is describing the distance of the spread of our scores, the distance from the mean. This is the measure of central tendency we're using. And the purpose of it, again, is just describe what's going on. How is our data distributed? Is it more clustered or is it more spread out? And this kind of tells you how, measures how well an individual score represents the distribution. So again, it's just providing more context to those measures of central tendency. So here's some examples of population distributions. On the left-hand side, we have height in inches, and then we have weight in pounds. And you can kind of see just looking at these, our graph on the left-hand side, a little more peaked, not it's a little more clustered together. So we don't see a ton of variability, maybe compared to our distribution of weight. We see looks to be a little more variability. We see the scores are more spread. Both are a normal distribution, but the spread is quite different for both graphs. So the four we're going to look at again, range, interquartile range. So these are very similar measures. We'll look at variance and standard deviation. Those are also pretty similar in terms of how we conceptualize and think about them. So even though we're talking about four different measures, the first two really fit together nicely and the second two fit together nicely. So range is just simple. We're going to start with range. It's probably the easiest one because all we're doing is taking the distance of our largest measurement from our smallest. So in this case, if you had this range here, we have a score of a 7, we had even a score of a 0 here. All you have to do to find range is take your high score and subtract it from your lowest score. So it just measures the total spread amongst your data. So an example of that might be, let's say on a pop quiz in a class, maybe in one of your other classes, the high score is a 92, the low score is a 34, the range, we just subtract those two and it gives us a 58. So the score's got a lot of spread there. Now, the problem with this, it does tell us the spread, but we're only taking into account of two scores, our high and our low. So this one is incredibly kind of like mean. It's very much sensitive to outliers. So the farther our data is spread apart, the more those outliers come into play, both on on both sides of the equation. Outliers, the big outlier, small outliers. So generally speaking, range, not the best measurement. It's kind of a poor measurement just because we're not taking into account, we're only bringing in those two scores and it's taking, those outliers are really, driving the bus, so to speak. So another way of thinking about range, again, smallest score to largest score. We want to get our data, arrange it from smallest to largest, then we just subtract. If it's a continuous variable, remember we go back, all of our continuous variables have an upper real limit and a lower real limit. All you have to do to find range in this case is subtract. But range always is max minus min. So we maximum minus our maximum value minus our smallest value. Based on all of our scores, we're not really accounting for all the other scores, so it can be kind of imprecise and not always the most reliable measure of variability. So good starting place, but it's not the best. So sometimes instead, what we might want to use is interquartile range, where we're measuring the spread that captures that middle 50% of the data instead. So instead of trying to capture both ends, the extreme ends, we want to really focus on that middle, and it becomes more resistant to outliers. So essentially, what you do to measure interquartile range is you're going to put your data in order, of course, and then you are going to divide the data into quarters, into four. We have quarter one, two, three, and so our median, that middle value, the middle is going to be quarter two, and it's going to be hinged by quarter one, our lower hinge, which covers the bottom 25% of the data, and quarter three is the median of the top half of our data, which will cover the top 75%. And all you have to do there, then at that point, pretty similar to range, we are going to take our interquartile range. We're going to subtract quarter three from quarter one, and that gives us our interquartile range. And it tends to be a much better measure of variability, especially when we talk about skewed data that's being pulled by those outliers. It's more resistant. It's much more focused on what's kind of happening in the middle of our data set. So here's an example of what that might look like in real life. We have this number. Now look at our scores. Like we have a 412 on one end and we have a 3 on the other. If you took the range of that, you're going to get what, 409 by subtracting 412 from 3. But we can use, this is clearly skewed. So what we can do instead is use our median as our measure of central tendency. And so in this case, we've got our median 13 right here, nice and pointed out for us. So how do we find quarter one? How do we find quarter two? Remember, we're going to use the medium of the bottom half and the medium of the top half to create those hinges. To create those hinges. Oops, sorry. There we go. Oh, I'm covering up my little spot. There we go. Sorry, I couldn't see myself here. I'll put myself over there. So we get 7 plus 1 divided by 2 gives us 4. Oh, there we go. Our hinges are fourth from the bottom and fourth from the top of the data. So we can see this is one hinge on this side. We're taking into account that 7. This is our second hinge, our upper hinge, in this case 21. So to find the interquartile range, all we got to do is simply subtract quarter three from quarter one, gives us a range of 14. Much different, telling us a much different story than us trying to subtract 412 from 3, getting 409 and giving us that overall range. Most of the data is kind of somewhere between 3 and 21. So as soon as we bring in this number 412, we're not quite telling the full story about what's going on with our data. So interquartile range, again, we're just breaking that up. We have four quartiles, 25th, 50th, 75th, and 100th. These are called this first, second, third, and fourth quartiles, respectively. We're dividing up. So I'm kind of just reviewing as I go along the way, dividing the distribution in four equal parts. Interquartile range is, again, quarter three minus quarter one. Scores fall in the middle 50% of the distribution. That's what we're more focused on. Sorry. There we go. So here's what that might actually look like with a graph. We're looking at here's the middle of the distribution. Here's our core, here's our lower hinge, which is 10.5. Our upper hinge is 13.5. We subtract that, gives us a interquartile range of 3. So a few different ways to kind of think about that. Okay, so we've looked at range, we've looked at quartile, we looked at interquartile range. Now we're going to switch gears and talk about variance and standard deviation. And these are both measures of finding the average distance from each of our observations that are from the center. So we're really looking at the average error. We're looking at the average distance from the mean when we talk about standard deviation. Variance is looking at the average squared error. Standard deviation is the square root of this. So if we know variance, we can find standard deviation. If we know standard deviation, we can find variance. But we're really talking about how much on average do our scores differ from the mean. We're trying to find an average of those distances. This is the equation for variance. Typically, you see variance depicted as s squared. So we have our summation symbol here. We're going to multiply that, or we're going to do in our parentheses first, of course, we've got to do our individual scores. So X represents those individual scores, each individual one subtracted from our mean. X bar is just our mean. We're going to we're going to compute that, square it, sum it up, divide it by n minus 1. Remember, n in this case, we're talking about population. So n is just the number of people in our population subtracted from 1. It might look scary, but hopefully it'll start making sense. Remember, variance is looking at that deviation. Sorry, it's kind of hard to see that bottom line there. But remember, we're looking at the spread of our scores and on how much that spread is occurring on average. That's what this is trying to compute. So here's an example. Sorry, these are all our individual scores. So let's say we've got our average is a 3. Our mean is a 3, and these are all of our individual scores. So you would take, to find the average, to find variance, you would take, 1 minus 3, 1 minus 3, 2 minus 3, 4 minus 3, 7 minus 3. Now, of course, these are going to come out to, they're going to come out, some are going to come out to negative, some are going to come out to positive. So what we have to do then is square those values. So that gives us 26, the total squared error. The larger this number is, the greater the error we're going to see, the greater the variability we're going to see. So, why can't we find the average error by calculating the distance between each score and the mean and add those up? Well, guess what? If we add them all up without squaring, it's going to end up giving us a 0. So if we don't do the squaring, that's not going to help us too much. Yeah, so we've got to square it. Otherwise, our sum of errors is going to be 0, and that's kind of suggesting we need to square the errors. Otherwise, it's going to look like there's no variation when clearly there is. So 26 is the total squared error. We would want to find the average square. How would we find it? That's where we're going next. We can use this equation. We use this equation. Basically, we've already figured out the numerator. This is the numerator. These are the individual scores right here. So that would be X. 3 is our mean. We're going to do that in our parentheses. Remember, we got to do exponent first. So we're then going to square those values. Then we're going to sum them. So remember, the steps, the summation notation, we've got to do it in the correct order. Otherwise, we don't get the right answer. And then we just plug 26 up top here. N minus 1 is going to represent the total number of our population minus 1. In this case, we have 5. So y n minus one, that's taking into account our bias and estimation. We'll cover that at a later chapter, so don't worry about that for now. But that'll give us, we have 26 on top, we have 5 scores, so we go 5 minus 1. What that really gives us is 26 divided by 4 gives us 6.5. So our variance in this case is 6.5. The larger that number is, the more spread, the more variation that's happening. Same thing with standard deviation. So standard deviation, what if we want to put it back? So remember variance, we're talking about squared error. We had to square these responses in order to get our error. So what about if we wanted to go back into our original units? Remember we're squaring, that way we can avoid 0. What do? We use standard deviation instead. So basically that same equation we just used, we throw we square root it. We throw the square root symbol over the whole thing. So now the same thing we just did, 6.5, we found our variance of 6.5. All you have to do is plug that in. Square root 6.5 gives you 2.55. So same thing. So now we have our variance in our original units. We're seeing the spread is on average 2.55 units distance from the mean. So, some other things about standard deviation. If we get a standard deviation of 0, what that is telling us is there's no variability. There's no data, or there's no error in our data. It's constant. Our standard deviation, like the mean, of course, is strongly influenced by outliers and also skewed distribution. So, kind of like we looked at earlier, interquartile range is really good for skewed distributions. There's those kind of trade-offs. The best measure, this standard deviation, though, is the best measure when we're talking about normal or close to normal and symmetrical distributions. This tends to be kind of the gold standard there. So it's probably the more common and most important measure of variability is standard deviation. It is a measure of the average distance from the mean, or sometimes referred to as the standard distance from the mean. And what it's doing is describing whether our scores are more clustered together or are they more spread out, or is there more scattered. And what we're doing, the calculations, of course, will differ from population and sample, which we'll get to later on. So variance, of course, is necessary to understand standard deviation, but they are not the same concept. So keep that in mind. And a lot of times when you're computing these things, you end up getting both. Like when you run your data through a program like SPSS, you actually get both. So it's not a big deal. How do we determine standard deviation? One, to determine the deviation, we need to find the deviation. We need to find individually how much our scores are differing from the mean. So in this case, we need to calculate deviation scores. In this case, this is our individual score represented by an X subtracted from mu, which in this case is representing our mean. So X minus mu. Then we find a sum of our deviations to use as a basis for finding the average deviation, the average distance from the mean. Two problems with this. Remember, if we sum all those up, they're going to add to 0. And if it's 0, that really what that's saying is we're not seeing any variation, but there clearly is variation there. So we need a new strategy. So what we can do is remove those negative deviations by squaring. So we're going back to that equation on variance. We're going to sum the squared deviation, sum of squared, and then average the squared deviations. And we're basically calculating variance. We are calculating variance first. Variability is now measured in squared units. So the average of the squared deviation minus the average squared distance from the mean. What do we do now to compute that standard mean? We need to, before we had those squared values, we basically need to capture variance and throw that square root symbol over it to get them back to our original units, taking into account those original units. So here's a nice chart if you want to, it might be helpful. So find our deviation, which is simply just calculating for each individual score, what is the distance from the mean? So you have your score sets, you calculate mean, and then you start subtracting from each individual one. You can add those deviations up and compute the average. However, it's going to end in zero, and that ends us there. And when we get to zero, that's saying there is no variation, but clearly there is. So what we do instead is we square each deviation. We find the average, again, find our variance. We take the square root of variance, and then we get, based on that, now we have our standard deviation, our average distance from the mean. So here's what this might look like visually. We have a mean of 6, and we then want to find out, okay, how much are these data points, how much are they varying from our mean? Like in this case, this data point of 1, it's got a distance of 5 units from our mean. This one here, this 7 has a distance of 1. This 5 has a distance of 1. That's what we're trying. So then once we have those distances, we want to find out how much on average the distances are occurring. So we're trying to collect data, we're trying to look at all the different distances each from each individual data point and then compare it to the mean and find the average. So essentially what variance really is our sum of our squared deviations divided by the total number of scores. SS just means sum of squares is the sum of our squared deviations, and there are two formula for computing sum of squares. We can sum it all up, x bar or x minus mu, square that. That's our variance formula there. We have this one over here. We have our definitional formula and our computational formula, if you want to use that as well. If we're wanting to find variance, yeah. So, you can use these two if you'd like. Definitional formula will find each deviation score. You're going to square it, then sum those all up. The computational formula, square each score and sum the squared scores. Find the sum of the scores, square it, divide by end. Subtract the second part from the first if you want to do it that way. You've got a couple different ways to do it. When using the computational formula, remember though, sum of squares does not equal summing all of your x's by squared. It doesn't mean sum of x, and so make sure you're following those steps. Make sure you're following the summation notation. Otherwise, you're just not going to get the right answer. So here's the formula if we're talking about for population variance. Remember, it's a little bit different for populations and samples. For a population, for variance, we're just taking sum of squares, dividing it by n. For standard deviation, then we square root that. So variance is the average of squared deviations. So we identify that with the population lowercase Greek letter of sigma. It looks like this here, squared, sigma squared. Standard deviation then is where we take that square root, so it'll just look like the symbol sigma here. Okay, let's do a quick learning check. Make sure you understand where we're at so far. Decide if each statement is true or false. Let's do both of these, and then you can maybe pause and make sure you understand. So, true or false, the computational and definitional formulas for sum of squares sometimes gives different results. True or false. And then true or false, if all the scores in the data set are the same, standard deviation is equal to 1. So once you feel like comfortable with the answer, maybe jot it down, pause the video, and then we'll come back. Okay, hopefully you've written your answer down or you have it in your head somewhere. First one, true or false? It is false. The computational formula is just an algebraic rearrangement of the definitional formula, so you should get similar results. Identical result, not similar, but identical, I should say. And then the second one is false. When all the scores are the same, they are all equal to the mean, so the deviation would be 0, not 1. 0 is the absence of variation in this case. All right, another learning comprehension check. Make sure you understand before moving on. The standard deviation measures what? Is it A, the sum of squared deviation scores? Is it B, the standard distance of a score from the mean? C, the average deviation of a score from the mean? Or D, the average squared distance of a score from the mean. Pause the video when you feel like maybe think it over, pause it, come back when you have your answer. Okay, in this case, the correct answer is B, the standard distance of a score from the mean, or the average distance from the mean in this case. Okay, so measuring variability and standard deviation with samples. So this is really going back to like day one. Remember, we are collecting data from samples so we can make inferences about our populations, because we most of the time we cannot collect data from the population. That's too time consuming. We just don't have enough time, money, resources, whatever. You know, so like you want to draw samples instead, and you're going to compute deviations, or you're going to compute variance statistics to try to understand what's going on with our sample to better understand our population. So remember though, our sample, it is limited information from a sample. We don't have the full scope of our data. Samples tend to have less variability, and computing the variance and standard deviation is the same as for a population would give. However, that would give us a bias estimate of the population values. So we want to be careful there. So here's what I mean by this is our population. We have a lot of spread versus this is the variability of our sample. It will not probably contain as much variability. It'll probably be similar, but it probably won't be exact. So we want to be careful about that. So in order to find sum of squares for our sample, we are going to compute the same thing we did before, sum of squares, and then instead we're going to subtract n minus 1, smaller n in this case is going to be, rather than big N for population, we use smaller lowercase n, and then we subtract minus 1. And basically the same thing to find standard deviation. You just square root that. You put a square root symbol over that, and you can find variance and then find standard deviation. We use an S instead of that Greek symbol for sigma when we talk about when we're talking about samples versus populations. So this is a histogram. We have 8 different data points, and this is just showing you, we have our mean of 6.5. 6 is only going to be half a unit from our mean. 11 would be 4.5 units, and then we could do that for all of these and calculate variance. We can calculate standard deviation. So, as far as some variability, thinking about sample variability, if population variance, we can compute it if we know the mean. Our deviations are computed from a known mean. Sample variation on an estimate of a population, though, this is what happens when we don't know, when the population is unknown. And so, in that case, maybe using our sample mean might restrict our variability. This is when we start taking into account what are called degrees of freedom, the number of our scores in the sample that are independent or free to vary. In this case, we will come back and talk about degrees of freedom later on in subsequent chapters. But this is where we take into account possible bias by subtracting 1 from that total number. That's why you do that in our sample versus our population. We want to take into account those degrees of freedom. Okay, let's do a quick check. A sample of 4 scores has a sum of squares that equals 24. What is the variance? Is it 6, or is it A, 6? Is it B, 7? Is it C, 8? Or is it D, 12? Pause the video. When you feel like you have an answer, come back and unpause the video, and we'll talk through how we found the answer. Okay, the correct answer is 8 in this case. So remember, if we go back to our formula, to find our variance, we want to take the sum of squares. So in this case, it is 24. We're going to go n minus 1. So we have 24. Our n in this case is 4. We have 4 scores. So we subtract 1 from that. That gives us 3. So essentially what we're talking about is dividing 24 divided by 3, which gives us the answer of 8. Now, if we wanted to find standard deviation, square root that. Okay. Let's see. Next one, true or false. We got 2 of those. True or false? A sample systematically has less variability than a population. And then true or false for the second one, the standard deviation is the distance from the mean to the farthest point of the distribution curve. So make sure you understand these, or write down your answer, true, false, pause, come back. Let's take a look at the answers. Here we go. First one is true. Extreme scores do affect variability, but are less likely to be included in our sample. And then false, the standard deviation extends from the mean approximately halfway to the most extreme scores. So not the furthest point in this case. All right. Let's see. Sample variance as an unbiased statistic. We're talking about unbiased estimate, a population parameter. Average value of our statistic is equal to the population parameter. Our average value uses all possible samples from a particular sample size. In this case, we're talking about N. Our corrected standard deviation formula, when we divide by N minus one, produces an unbiased estimate of the population variance. That's why we're bringing into account those degrees of freedom. A biased estimate of population parameter would systematically overestimate or possibly underestimate. So again, part of the reason why we use that N minus one instead of just the normal N. So here are some examples of what, kind of looks like if we're taking into account, we have a sample of 9. We have different scores here, scores, first score, second score, our statistics, our mean, our unbiased mean, of course, 36. Our bias variance gives us a 63. Our sample statistics unbiased variance gives us a 126. If we want to use the mean of 9, an unbiased sample mean gives us a 36 divided by 9 equals 4. Biased giving us a 7. Unbiased sample variance, 14. So it tells us different stories depending on whether we're talking about a biased or unbiased mean. Oops, sorry. There we go. More about variance and standard deviation. Mean and standard deviation are particularly useful, especially when we're talking about graphs of distributions. They kind of tell more of the story. Mean and standard deviation together, they're what kind of give more context to those descriptive statistics that help us describe the distribution, the characterization of our distribution, like how spread out is it. When we're talking about population and samples, it's easy to represent mean and standard deviation. You have your vertical line in the center that typically denotes the mean, and the horizontal line to the right, left or right, denoting standard deviation. So you might see it depicted this way. Here's our mean, and here's variance. Here's our mean, and we're looking at our spread of our score over here. Yeah, so there's a couple different ways you might see that depicted. What happens if we transform our scale? If you add a constant to each score, it would change the mean, but it wouldn't change the standard deviation. However, if we multiply each score by that constant, the mean is going to be changed and the standard deviation will be changed as well. So essentially what we're doing is we're multiplying the standard deviation by that constant. So meaning like if you add 1 to every value on your data set, the standard deviation would not change. But if we multiplied everything by 2, for example, that would be the constant in this case. That would change our deviation and our mean scores. Okay, so standard deviation is describing the score in terms of its distance from the mean. We describe the entire distribution with 2 numbers. We have the M in this case and S, mean, standard deviation, or variance. Referring to both allows us to construct a different kind of scales of measurement. And we'll go look at 4.11 here. Yeah, we have a sample mean of 36. We have 20 scores, and we have our variance of 4. We can kind of see that depicted here, vertical line for our mean, horizontal line for our variance. Okay. In terms of, remember, inferential statistics, remember we're trying to make inferences about our sample statistics to the population, detect meaningful and significant patterns in our results. And what variability does is really it helps us see the patterns. Like picking up variability kind of allows us how easy it is to see patterns in our data. If there is high variability, it might obscure the pattern. If lower variability might kind of help us see more of a pattern. There more reason why we use this stuff. Okay. So here are some examples of, what it might looks like, experiments. We have high and low variability. Here we can clearly see the pattern going on in terms of the variability. Treatment A, treatment B, there's clearly something going on here. Most of the data for treatment A is clustering here in this, part of the graph. Treatment B on this side of the graph. Versus if we look at here, we see more spread here, but it's really harder to pick out a pattern. It's much harder to pick out that pattern. Even if we're talking about the same means, the spread of the scores kind of it tells a different story with our data, and that's again the whole purpose of using these measures of variability is to tell more of the story of what's going on with our data. Okay, so let's do another quick learning check. A population has a mean of 6, and we have our variance, or excuse me, our standard deviation of 2. Each each score is multiplied by 10. So what is the shape of the resulting distribution? So you can go A, you got a mean of 60 and a standard deviation of 2. B, mean of 6, standard deviation of 20. C, mean of 60, standard deviation of 20. D, mean of 6, standard deviation. Oops, sorry. Need more coffee, apparently. Standard deviation of 5. So pause the video when you think you've got an answer, come back, and we'll resume. Okay, in this case, what we're talking about, multiply means we are multiplying by a constant. So we are multiplying both values by 10, and that would give us C. Our mean is now 60, and our standard deviation now is 20, once we have applied the score that way. That is a constant. Okay. Next one, true or false? A bias statistic has been influenced by researcher error. And then number two, in this true or false, on average, an unbiased sample statistic has the same value as a population parameter. Pause the video. Once you feel like you have your answers, come back and we'll take a look at both. Okay, welcome back. First one is false. Bias just simply refers to systematic effect of using sample data to estimate the population. Like there is going to be probably some gap between sample to population. So that's all we're talking about is deviation. We're talking about error, not because some researcher made an error, but because simply there is bias going from sample to population. The second one is true. Each sample statistic differs from the population parameter, but the average of all samples will equal that parameter over the long haul, taking the averages. Okay, this is what SPSS, if you were computing standard deviation based on your data set, this is what it's going to look like. And how do you interpret that, when you compute this? So we have a variable here in this case. Our n equals 8. We have 8 scores. We have a range of 8, meaning our maximum value is an 11. Our minimum value is a 3. You subtract those and it gives us our 8. Our mean, of course, is 6.5. Our standard deviation and our variance are depicted here. You have 6.857 at 714 as our variance. Define standard deviation, excuse me. You just square root that value, and there you go. And that's what I mean when you're computing these statistics with a computer program like SPSS, for example. Luckily, it gives you all that stuff. It's pretty rare that you would, just need range or just need standard deviation or just need mean. Typically, you're going to have them all at your disposal. But in terms of what information you present to the public or whoever that information is intended for, some values are going to be better than others in terms of trying to tell your story about your data. So that's chapter 4 in a nutshell. Kind of went fast, but if you have any questions or concerns at all, please don't hesitate to reach out to me via email, reach out to me in my office hours, and we can talk about any of these ideas. But that's it for chapter 4. That's variation. So I'm going to go ahead and stop here, and I'll see you on the other side for chapter 5. Take care. Bye.